Alright, welcome back everyone. It's been a couple months since my last video, so partly for myself, I'd really like to recap how we got to where we left off. So, to kind of go back to the beginning, we were looking at, we started off with the REST actions. I believe I targeted REST index action, where you put or post to an index name a document. But of course, there are other indexing operations that users can use. There's the index delete, update action, and of course the one that you're most likely to use is the bulk action, just because it makes sense to send multiple updates at once. But if I recall correctly, we started off looking at index action and saw that every REST action ends up calling into some transport action. So REST index action calls into transport index action, which is marked for deprecation along with transport delete action. Both of those extend transport single item bulk write action. I believe the deprecation is intended that really what we should probably do is just go kind of directly like this, right? So REST index action should directly call transport bulk action without going through these extra hops. Now, the extra hops are very lightweight, so they don't really hurt anyone. I didn't really go into updates. There is some overlap, but things are a bit different. So we spent a decent amount of time in transport bulk action. Note that all of this stuff is running on the coordinator node. So that's the node that received the request. Now, transport bulk action, as part of its operation, it'll go through all of the individual index operations that you're trying to perform. And if it sees that any of them are targeting an index that doesn't exist, but we're allowed to auto-create indices, then it'll forward a call out to the cluster manager to say like, hey, please create this index. Wait for that to respond before proceeding. So the transport bulk action on the coordinator, for each target shard, will issue a network request or a transport request out to transport shard bulk action. Now, transport shard bulk action, if I recall correctly, because we wanted to get down to where it actually calls into Lucene, I believe I looked at what happens with the perform on primary. Now, one consequence of perform on primary could be that as it goes through and does these things, it may get back a response that a mapping update is required if you have dynamic mappings enabled, and an index operation that's being performed contains a new field. Then before we can proceed, we have to go talk to the cluster manager, because the cluster manager is the final arbitrator for what fields exist in an index. So we have to go notify the cluster manager that we would like to add a field, and then that comes back to transport shard bulk action, and then it's allowed to try again to do the primary operation. So this perform on primary ends up calling into this class called index shard, calling its apply index operation on primary, which ends up calling the index operation on engine, which within that we'll call index into Lucene, which then calls add docs or update docs, depending on which we're doing. If we're append only, then it's add docs. And then that's the thing that actually talks to the Lucene index writer. Now, the thing is, this transport call doesn't directly call perform on primary. Really, what happens is actually a fair bit more complicated, and this is kind of what we got into in the last video. So transport shard bulk action is a subclass of transport write action, which itself is a subclass of transport replication action. Now, transport replication action has the do execute method that gets called when the request is sent from the coordinator. So that do execute method, first, transport replication action in its do execute will try to do a so-called reroute phase, just in case the target shard isn't here anymore. And so if that's the case, it'll reroute it to the correct shard and kind of repeat. You could imagine, hypothetically, a shard that's moving very quickly. The requests keep hopping from node to node. And then the node kind of says, sorry Mario, the shard is in another castle. But under normal circumstances, because we've landed on the correct node for the primary, this perform action, the reroute phase will end up going down a path of perform local action, which ends up doing a localhost transport call to this method that was registered by transport replication action to handle that local callback, well, that local transport request. So we end up with this handle primary request, so this async primary action, reroute phase, primary shard reference, these are all inner classes of transport replication action. Quite a big file. But async primary action do run, as we end up here, so that ends up creating a replication operation, and the replication operation will call this primary shard reference perform method. I don't know why I switched between using dots and using the octothorpe. Yeah, these are functionally the same thing. It's just indicating we're just invoking an instance method. So, the long way that we end up actually getting to the perform on primary is via this calls the method shard operation on primary, which is declared in transport replication action, and implemented in transport write action. And the implementation in transport write action calls dispatched shard operation on primary, which is then implemented in transport shard bulk action, which calls that perform on primary, which does that stuff that we talked about. And then all this stuff comes back, and the callback, the listener for primary shard reference perform, is this callback, which is replication operations handle primary result. So that's where we left things off last time. Phew! So yeah, I hope this helps clarify some of the content from the earlier videos. It certainly helped clarify it for me. So let's get on with it. Let's pick up where we left off. We were here in handle primary result in the replication operation class. So we've got some type of primary result. This type is given by the class that called us, so from replication operation, the type of primary result ends up being defined by whatever the primary is, whatever the listener is. So in this case, in transport replication action, here we've got our action listener, where we've got some response listener that was passed in. Oh, no, sorry. Where's the type of the response listener? So we adapt the response. Sorry, I want to figure out what the type of the primary result T is. So, what class? Response, okay. So this result, no, that's for the replica request. So, maybe I'm going to lose too much time looking into this. Transport replication action, let's skip that for now. I'm not sure what the type is for the primary result T, but we'll just have to take into account that the primary result type produces some kind of replica request. So in this case, I believe the replica request is derived from the transport shard bulk action is what defines what the replica request is and what the primary request is. And then the primary result T is the thing that ends up mapping to whatever the replica request is. If I recall, I remember looking into this code a little bit recently, and I believe that the transport shard bulk request executes on the primary and then again on the replica. So it's essentially just propagating the type. There are some other replication operations that do a type transformation between what happens on the primary and what happens on the replica. But in this case, because we're just trying to propagate the indexing operation via the transport shard bulk action, the request to that. So yeah, we just kind of push it through. So in general, the replica request is not going to be null in this case. I recall that the only time that the replica request is null is if the primary operation failed for whatever reason. You know, maybe the primary ran out of disk or something happened such that the primary index operation couldn't proceed, in which case we don't want to replicate that. So, down here, okay, so a key thing is we get the replication group, and there's a note here that we have to get the replication group after successfully indexing into the primary in order to honor recovery semantics. We have to make sure that every operation indexed into the primary after recovery start will also be replicated to the recovery target. If we use an old replication group, we may miss a recovery that has started since then. We also have to make sure to get the global checkpoint before the replication group to ensure that the global checkpoint is valid for this replication group. If we would sample in the reverse, the global checkpoint might be based on a subset of the sampled replication group and advanced further than what the given replication group would allow it to. This would entail that some shards could learn about a global checkpoint that would be higher than its local checkpoint. I'm not entirely clear on the global checkpoint semantics yet. I believe it's essentially about kind of linearizing operations, that this global checkpoint is steadily increasing, and we generally want operations processed on the primary to be processed in the same order on replicas, I believe. In particular, if you have an update operation, it may be significant that the update operations get processed. Well, yes, it certainly is significant that update operations get propagated in the same order, I believe. Yeah, though, I suppose the way that updates get resolved on the primary, to the best of my knowledge, is that it computes the new document and then processes it as an index operation in the end. So it ends up being sort of an upsert. So it will overwrite the existing document by, inserting the new document. So maybe that is safe to process on the replica out of order, provided that we've computed versions properly. I'm not sure. So, the replication group, though, let's look into how that gets resolved. If I recall correctly, this primary here, so this is the replication operation primary, which ends up pointing back to that primary, the primary shard reference, I think it's called? Which, if we go down to the implementation, so we've got this primary shard reference in replication, in transport replication action. And this holds a reference to the index shard of the primary. And index shard is, you may recall when we were getting into the engine and the index shard, that they're sort of intertwined. They're fairly closely coupled, probably more coupled than perhaps they should be. With this replication group, it gets it from the replication tracker that the primary has. And so here's the replication group. It's just a volatile member. I can't see the volatile keyword when I hover. I'm getting a pop-up that is not getting captured in the recording. So replication group is volatile. It gets updated down here in update replication group and notify, and this calculate replication group, if I recall correctly, we end up relying on the routing table. The routing table comes from the cluster state. So the cluster state says, for this shard, here are all of the copies of the shard, all of the placed copies, which nodes they get routed onto. And for each of those shard routings, as they're called, it says, this shard is mapped to this node as a primary or a replica, or now a search replica, if you have writer searcher separation. So, we return this, so the replication group came from the cluster state. I forget what triggers the update replication group and notify. A bunch of things. So we probably aren't going to look into all of these, but I suspect at least one of them, probably this one, gets triggered, update from cluster manager. So in this case, we've received new cluster state from the cluster manager, and then we update the routing table accordingly. This is sort of a little bit related to the communication between nodes and the cluster manager. Okay, so as I said, the replication group ultimately, I believe, pretty much just comes from whatever's in the current cluster state that the node hosting the primary sees. So, if we go back to handle primary result, we've got the replication group, right? Because this is coming just from the shard routing, I didn't see when the replication group, this is going to bug me. The replication group, when it's constructed, so it's given the routing table, I guess so we have the full routing table, right? But then we have replication targets. I think this may be relevant to specify, my dog's spooked by something. So the replication targets should probably exclude the primary and exclude any search-only replicas. Sorry, just gonna let the dog out. Okay, go bark out there. Okay, so let's see. I'm just kind of curious about this. So we add Okay, so if the shard is unassigned or search only, we mark it as skipped. Curiously, I don't see any check here. Maybe I'm missing it. Like it feels like the primary itself could get added as a replication target, which doesn't seem right, because the primary itself should, like we don't want it sending the index operation back to itself. Maybe that gets filtered out further down the line. So let's go back to replication operation, handle primary result. So we've got the replication group, and we call this perform on replicas. So this is where, okay, we've got our replica request, which, as I said, I believe, I'm not 100%, but I believe this is the shard bulk operation. Or, sorry, the shard bulk request, I guess, which is the input to the transport shard bulk action. Now, down here, this is a little bit confusing. So, as we go through all of the replication targets, which, again, so we've got the primary routing, we construct this proxy request. I spent a little bit of time diving into what's going on with this replication proxy. It turns out that there are a couple of different implementations of the replication. The default one is fan-out replication. That's the one that we're going to look at today. But there are some others. Let me just remind myself. No. Okay, so we construct the replication proxy request, which ends up holding the shard routing, the primary routing, etc., including the replica request, the primary term associated with. Oh yeah, the primary term for fan-out, we're not going to look at that. But one of the replication modes is related to remote store-based replication, where what gets sent to the replica isn't the actual request, but instead we notify the replica that there's new data available on the remote store associated with some primary term. I'm fuzzy on that, but let's see. So we get to this, perform on replica proxy, and then this is the thing, that ends up being either the fan-out replication proxy or this new as of 2 years ago, I think, this replication mode aware proxy. This is the one that says we're either doing so-called full replication, and if I look at the comment here, yes, so full replication in this mode, transport replication action is fanned out to underlying concerned shard and is replicated logically. In short, this mode would replicate the replication request to the replica shard along with primary term validation. And then there's primary term validation where it's fanned out to the underlying concerned shard and used for primary term validation only. This request is not replicated logically. So I believe that's the one that's relevant to remote store replication. But so as I said, the one that we're going to end up in is fan-out replication proxy. And the way that this thing gets constructed in this method, this is run with primary shard reference. So this was one of the things that we called before. When we constructed the replication operation, way back, when we constructed the replication operation, before it sort of went through all those hops that eventually took it to the transport shard bulk actions perform on primary, which then called into the index shard, which called into the engine and indexed the documents, performed each of the bulk operations. So here we tried to decide, do we use the replication mode aware proxy or the fan-out replication proxy? So again, we only use the replication mode aware proxy if the index shard is assigned on remote node. So again, this is just related to remote store, which I'm not going to concern myself with today. That's a subject for probably multiple other videos. So anyway, in this fan-out replication proxy, when we get to perform on replica proxy, so we have when we were constructed, we got a perform on replica consumer, which was the last argument. The last argument? I guess. So we've got the replicas proxy. Where was the consumer? Oh, perform on replica consumer, which was passed into perform on replica proxy, which calls into, So ultimately, this whole thing is sort of a very roundabout way of essentially saying, For each shard, we're essentially going to call this method right below us. So we've got the proxy request, which I guess is a form of Replica's proxy consumer? Is it? No. No. Perform on replica proxy is the thing that, yeah, propagates in the proxy request, and the proxy request contains the real request. Right. Yes, right here. So we get the actual underlying replica request, and this is the thing that I believe we're going to propagate. So, not entirely sure what the pending replication actions is for. So we were here in perform on replicas, and then we eventually got into perform on replica. Okay, yeah, I don't know what this pending replication actions is going to do, but we'll see. And, of course, because everything's asynchronous, we're going to have a replication listener, so this is what will kick in once the replication is successful, or if the replication failed. If the replication fails, I guess, yeah, we'll sort of take that as, like, maybe this is a sign that the replica shard is down somehow. And so, yeah, we'll check, to reach out to the cluster manager to get the latest shard state, then report. Maybe here we check to see if the nature of the exception is that the shard was not available. And yeah, we populate some shard replica failures. So yeah, possibly this will, and then down here, see we have this replica's proxy, fail shard if needed. So yeah, maybe this is kind of a circuit breaker, that if too many operations to the same replica failed, then perhaps we mark the shard as failed. I suppose that would have to go back to the cluster manager, because the cluster manager should be the source of truth for that. Anyway, so we construct this retryable action. So this will call that replica's proxy consumer, and then we're going to run it, which I believe the run implementation for a retryable action should be try action, I would assume. Retryable action, it has a run, which, so creates a runnable, and and the runnable will try the action. So that implementation of try action was replica's proxy consumer. It accepts with the listener. So the replica's proxy consumer, so this was passed in, that consumer was, so that's the final argument, which is the perform on replica consumer, which was passed into perform on replica proxy. Sorry, I feel like I'm going in a circle here, that we've come back to perform on replica. Yeah, because the perform on replica consumer. So let me go back to replication operation, perform on replica. Well, this can't be, a reference back to itself, I'm sure. So this thing, this is the perform on replica consumer, which is the thing that calls that. Sorry, I'm losing a little bit of time here. So this is the thing that calls out in the fan out replication proxy. So our final argument, it's the proxy request. Okay, so the proxy request is the thing that, is the final argument. Get replica's proxy consumer. Okay, so this is proxy perform on. Okay, got it. Okay, so we've got this replica's replica request. So this is a proxy. So this is the thing that we're actually going to do. Phew. Okay. So this instance of replicas. So I believe we've got an instance of replica's proxy. Yeah. So this is the thing that we're doing in the retryable action, is that we're calling this perform on, because the accept called perform on. And so, so we've got a particular replica, we've got the request that we want to propagate. We end up wrapping the replica request in this concrete replica request. I'm not entirely sure what that's about. We set up this response handler, which ends up taking the listener, and we wrap the response that we get back in a replica response, I believe. And here we call transport service.send request, where we have the string for the transport replica action. So we note the transport replica action is not an argument to the replicas. It's not a constructor argument to the replicas proxy. So this is being inherited from the transport replication action. So this is set up in the constructor for transport replication action, right? Which is ultimately just the action name with a replica action suffix. So I believe back when we were looking at the transport shard bulk action, we saw that transport shard bulk action has, let me go back to that, transport shard bulk action, right? So remember, transport shard bulk action extends transport replication action, right? Yeah, because it extends transport write action, which extends transport replication action. So this one has an action name, which is indices data write bulk. So this is the action that executes on the coordinator, is indices data write bulk. It lands on a shard, and then it gets a square bracket S appended. And then, for the primary operation, it gets a square bracket P appended. So then when it's a replica, it gets the square bracket R appended. And this is significant because in transport replication action, if I recall correctly, we end up binding. Okay, so this is used, yeah, so we've constructed this string, the transport replica action string, right, where it's the action name, square bracket S, square bracket R, and this is bound into a request handler. So what happens is when it lands on the replica node, we're saying, once I get this operation that's indicated by, what was it, indices data write bulk, I think, square bracket S, square bracket R, and it's like, aha, I'm going to hand it off to handle replica request. So, yeah, there was a similar sort of thing with how the primary request got wired in, right? And that's where you may recall from, the quick recap at the start of the episode that there was this whole thing where the replication operation ended up calling into something, which ended up doing sort of this local node primary operation, which then could reroute if the primary moved. But in this case, we're going to go instead into handle replica request. So this is the operation, the transport shard bulk. Well, so we're in transport replication action, but remember, that's the base class. Really, we're in transport shard bulk action in handle replica request, which we'll call, okay, so we've got this async replica action that we create. So the async replica action, okay, so we've got the replica request. So this one, being an action, sorry, I'm going to jump over here to expand out the structure. So it's an action. Actions are runnable. Yeah, we call run on it. And run ends up calling do run. So if I recall correctly, basically run calls do run and then takes care of like listener sort of stuff, I think. Something like that. It's going to bug me if I don't see it. Abstract runnable. Oh, okay. So this is just to trigger the on failure and the on after. Yeah. Yep. Okay. So we're going to acquire the replica operation permit. Okay, so the replica here is an index shard. We've got the request. On acquired, so we're saying we're going to acquire the replica operation permit, and once we've done that, call me. That this here is the third argument, which is the onAcquired listener. So we're going to call replica acquire replica operation permit. So now we're going into the index shard class, right? So inner acquire replica operation permit, and again, we're going to propagate in that listener, and I'm pretty sure we're going to come back to that. Well, obviously we're going to come back to that async replica operation, or async replica action, and that should be the one that actually performs the replication action, which I believe we're going to eventually see it call back into transport shard bulk action, but we're not there yet. So what I'm really curious about is where does this on permit acquired happen? So we're gonna set up another listener where what this listener is going to do is it's going to handle failures, right? If we're successful, we're just going to call on permit acquired. But if we fail, yeah, we're going to do this stuff. Okay, so we're going to potentially update a global checkpoint on the replica, potentially advance the max sequence number of updates or deletes. Not sure what this is doing, but let's focus on the happy case for now. Let's assume that we're not failing yet. So here, where we're trying to acquire the replica operation permit, so we synchronize on a mutex. The mutex is held by the index shard. So at this point, we're sort of locking the index shard against anything else that could affect this mutex, or that may also block on this mutex. So I think the goal here is to ensure that only a single replication object is targeting a replica shard at a time, which, considering that a shard should have a single primary and multiple replicas, each replica should only be receiving replication operations from a single primary, and so those should probably be linearized. Perhaps this is just this mutex in case the primary could be handling requests on multiple threads. So possibly what we want to handle is like multiple replication requests coming from the primary and ensure that they get sequenced on the replica. So that's interesting though, that we acquire this lock, and what I want to get to is, again, where do we call that callback? Because, as I said, I'm pretty sure that callback is actually where the action's going to happen. So we've got the operation listener. So where do we use the operation listener? Oh, okay. So we've got the operation executor. So the operation executor is, it was passed into us. Oh, weird. Okay. So, curiously, the operation executor gets triggered after we've released the mutex. So perhaps the only stuff that we have to do under the mutex is to bump the primary term. So bumping the primary term refers to when an index is created, all shards are allocated initially with a primary term of 0, I believe, when no primary has been allocated. And every time that a copy of a shard becomes a primary, we increment the primary term. So again, in the happy state where nothing ever fails, when you've allocated a primary, that primary has primary term 1. Meaning it's the first time that we've ever allocated a primary for this shard. If that primary fails and we promote a replica to being primary, we'll bump the primary term up to 2. So, so we're mostly within the mutex, see? Oh, and we're doing a double checked lock. I didn't notice that. So, I think what we're doing is we're saying, if the primary term has changed, I suspect this require primary term update is that the operations primary term is greater than the shard's primary term. So the replica, remember, has to know the primary term of the primary that it's receiving updates from. And so if there's been a failover, if another replica has been promoted to primary, all the other replicas need that information, right? They need to know, there's a new primary in town. And I believe it may ignore things coming from the old primary. That part I'm a little bit fuzzy on in terms of how exactly failover executes end to end. But so see, if the operations primary term is greater than the pending primary term, which I assume is like the current primary term. So, okay, cool. But then otherwise we call this operation executor. So let's go back to where we were acquiring the permit. We have this inner acquire permit. Who calls inner acquire permit? Sorry, I'm jumping back. Who calls this? Okay, so this was acquire operation. Okay, so, interesting. So, so we haven't actually acquired the permit yet. The thing that acquires the permit is this one. Oh boy, right? Because all we did here was, we potentially bump the primary term and stuff, but then we call this accept, which is just this consumer, and this is the thing that we'll actually acquire. And, yeah, but oh, okay. And we call it with the onPermit acquired. So the onPermit acquired gets passed into inner acquire replica operation on permit, and then that's the listener that gets passed into the consumer here. Okay, so we want to go to this acquire, which calls another acquire. Again, I'm mostly interested in the onAcquired. So, again, we're going to do this delegate failure. So, on success, we're going to do this context preserving action listener. Oh, so this is related to the thread context. I could be mistaken, but usually what I've seen is that maintaining the thread context is very important for preserving permissions. So essentially what we do is the security plugin, for example, will initialize a thread context when the request comes in and make sure that it uses that thread context. But if something is going to be queued up, so in this case, yes, if we have queued block operations, I believe that's saying like, nope, we can't actually do the thing now that we've got some kind of block on the index, and so we're going to queue it up. We're going to park it, right? Which presumably means we want to release the thread. So we don't want to hold the thread context in the thread. That's, I believe, why we need this context preserving action listener, because we're going to stash this as a delayed operation to be done later if there's a block. But again, let's assume we're not blocked. So we're synchronized on this. Where's the synchronized block end? Oh, okay, and then else we do this just acquire. I am a little bit curious about like what the index shard operation permit acquisition is. Ooh, so there's some kind of semaphore that we try to acquire. Okay, so we're trying to acquire a single permit. How many permits? Oh, interesting. There can be a lot of permits. It seems that total permits defaults to integer max value. So, fair to ensure a blocking thread is not starved. But yeah, if the total permits is essentially infinity, I need to look into this a bit more to see how these permits get handled, because it does look like, yeah, it's just unlimited permits. I wonder if this is something that's changed over time. I do see. No, if I look at the commit, clarify requiring index shard permit, I'm kind of skimming through the text here. I don't see anything, there's nothing that's jumping out at me that suggests that something was changed to say, let's allow unlimited permits. That's interesting that, unless I'm mistaken, this is not limiting us to a single shard operation. Yeah, we did single thread it via that mutex to make sure that only one thread is bumping the primary term at a time, which makes sense. But yeah, that's interesting that we seem to allow kind of unlimited permits. So, now we go back to the onAcquired, where we have to go, I think it was back to index shard? So, again, we wanted to go into the thing that gets called, replica onAcquired, and so we're going to actually finally call the onAcquired, which was the async replica action. Okay, so because it's a listener, we invoke its onResponse operation. Now we know what this releasable is, though. This releasable is the permit that we acquired, right? So, and presumably, so here, if there's any exception, we close the releasable while handling exceptions. Same if there's an exception here, same if there's an exception here. I wonder, how do we release it when in the happy case? Oh, here. Yeah, okay, here's where we release it. And so it says that we're releasing the shard operation lock. Yeah, maybe I'm misunderstanding the behavior of the semaphore. We don't use semaphores in Java. Sorry, I have to... How do you spell semaphore? Sorry. We were in index operation permits. Yeah, index shard operation permits, where we've got the acquire, the semaphore, which is of type semaphore, Java util semaphore, the int,
with a given number of permits and a counting semaphore maintains a set of permits. Each acquirer blocks if necessary until a permit is available and then takes it. This is what I thought, that normally you have some cap on the number of operations that can run concurrently, and each time that you take one, you decrement, and each time you release one, you release it, and then this way you can guarantee that no more than n operations are running at once. Curiously, given that we set the maximum to integer max value, these permits seem kind of useless. Just because we allow as many as we want. Huh, that's weird. Okay, so we're back in transport replication action, in its inner async replica action, in its on response, and we call shard operation on replica. Now, assuming this is the same pattern that we saw on the primary write, I believe this method here is going to be defined in transport write action. Yep, so it's abstract, it's extended in transport write action. It's not extended in transport shard bulk action. But what this will do, so it'll make use of an executor. I'm trying to remember if shard operation on primary also uses an executor. Yeah, so it's the same pattern, right? So we figure out which executor we want to use. This time, we don't actually even have to decide which executor we want to use. We just use, here, it's the same thing, it's just here, the executor is actually assigned to a variable, here it's just inline. Okay, cool. So it's the exact same pattern as shard operation on primary and shard operation on replica. Cool. So, very, very similar structure. And so now we go into dispatched shard operation on replica, which, again, is abstract on transport write action, but is implemented in transport shard bulk action. So now we're back in transport shard bulk action, which, that implements the abstract method, but mostly just delegates to perform on replica, which, again, this is very similar to when we saw dispatched shard operation on primary. Okay, we did a little bit more with the perform on primary, mostly because we needed to handle the mapping update listener, right? So, if you're doing an operation on primary and that we got a mapping update, so if there was a mapping update, then we're gonna invoke this update mapping on cluster manager and listen for that response. Cool, and then we're going to retry the operation once the mapping's been updated. So, again, this is how dynamic mappings are handled. The good news is the dynamic mappings only need to be handled on the primary, because if the primary updated the mapping, we know that the mapping has already been updated by the time we hit the replica. So, I wouldn't be surprised if there's something in the logic here where we end up calling similar logic to the primary, and if we see, I wouldn't be surprised if we'll see something where there's some invariant check that confirms that we definitely don't want to see a mapping update on the replica ever, because that means that something went wrong. So, okay, cool. So we iterate through each of the bulk actions, bulk items. So it's worth noting, just to clarify here, we received a bulk operation on the primary, which is a series of individual operations. Index this document, delete this document, index this, index this, index this. So that's the shard bulk request of a bunch of operations that are all going to be applied to the same shard. That whole bulk action was replicated, right? So it's worth noting that while we process them as the individual operations in the current Java process, when we replicate out to the replica, it's not that we replicate each of those little operations, because that would be a bunch of back and forth network calls. Instead, we execute all the operations on the primary, and then take that same batch of operations, presumably excluding any failed ones, and we propagate them out to the replica. Incidentally, and when I said excluding any failed ones, I guess technically we don't exclude them, we send them along, and I guess here, see that, they were failures on the replica. And I think this has to do with this mark sequence number as no op. I believe this is sort of ensuring that the primary and replica agree on which operations did what. So if an operation failed on the primary, on the replica, we're going to mark that same operation as having happened, but didn't do anything, because we're not even going to attempt it on the replica. In particular, it would be really bad from a consistency standpoint. If the operation failed on the primary, we did try to do it on the replica, and it somehow succeeded, that now the replicas are sort of ahead of the primaries in a way. Yeah, that would be bad. So, otherwise, if the primary operation didn't fail, then for this individual item, we're going to call perform on replica. So we're already in a method called perform on replica, but this is the one that's taking the full bulk shard request. Now we call this perform on replica, which contains just a single item, right? So now for the item, we're very similar to, this one was called perform on replica. This one is called perform op on replica. And so curiously, we don't do the same thing for the primary. On the primary, how do we, somewhere else we end up iterating through, we call this execute bulk item request. Yeah, so we're saying we have more operations to execute. Oh yeah, because there's this whole bulk primary execution context. And yeah, this is the one, okay, so this is where we're doing the loop, right? But it's with this, the iteration is handled by the bulk primary execution context, right? So we're just sort of saying like, okay, give me your next operation, give me your next operation, give me your next operation. Whereas for replica, it's sort of more direct, right? That we're literally iterating through the items with a for loop, not a while loop, and we perform each operation. And very similar to the primary though, that we convert the doc write request into, we cast it to the relevant type, and here we call replica apply index operation on replica. So this is calling into index shard, and this ends up calling into the same apply index operation. So once we've reached this point, we're kind of converging the replica and primary code, right? Because once we've gotten down to this level, it's just, I need to give the engine this write operation, and I want it to perform it. The engine, if I recall correctly, doesn't really care that much if it's operating on a primary or replica. It's just the thing that's gonna talk to Lucene and perform the operation. Note that in this case, it is actually significant that here we call apply index operation. Here we are saying like, well, let's look at this thing, and because we're a replica, if we land here and we've got segment replication enabled, we don't actually want to index the thing again, right? Because that was the whole point of segment replications. We're just copying segments around. But we do still, apparently we can still propagate the individual operations. I believe this is so that they get propagated into the translog, perhaps? But, yeah, I remember we got into something about having a plan, having an index operation plan, and that plan determines whether or not we index into Lucene or not. It is worth noting that, we override the parsed document, I believe, right? Because here we call docmapper. In the normal non-segrep case, down here we end up doing the document parsing. Curiously, here's where we can get that index result if there was a mapping update. I'm a little curious, while we're on the replica path, popping back here, we're in apply index operation on replica. So we've got this result. Okay, and then we break out. Yeah, sure enough, there is a check, as I thought, that again, it should never be the case normally that something lands on the replica and requires a mapping update. This long comment here seems to suggest that it could happen. So I'm just going to quickly read this. Even though the primary waits on all nodes to act the mapping changes to the cluster manager, see mapping updated action, update mappings on cluster manager, we still need to protect against missing mappings and wait for them. The reason is concurrent request. Request R1, which has new field F, triggers a mapping update, assuming that that update is first applied on primary and only later on the replica. It's happening concurrently. Request R2, which now arrives on the primary, and which also has the new field F, might see the updated mapping on the primary and will therefore proceed to be replicated to the replica. When it arrives on the replica, there's no guarantee that the replica has already applied the new mapping, so there's no other option than to wait. I was under the impression, though, that the primary sort of makes the call out to the cluster manager and waits for the cluster manager to propagate it back. But, of course, I guess the cluster manager is propagating out to nodes one by one. Maybe it propagated back to the primary, but hasn't propagated out to the replica yet? Perhaps. That's puzzling. Yeah, I would have thought, though. Well, yeah, and it says, even though the primary waits on all nodes to act the mapping changes. Yeah, I thought that it's only once the cluster manager has said, like, yes, everyone has the new mapping, that the primary can proceed. But, yeah, I could be mistaken there. Evident, clearly, the fact that this check here is good just from a sanity standpoint anyway, right? Make sure that we're not accidentally ending up in this situation. I suspect it's extremely rare. I'd be very curious to see if this gets logged and see how frequently this ends up happening. My hunch is not often. So anyway, where were we? We were on apply index operation on replica, which just calls apply index operation, which this is code that we've seen before. In the non-segment replication case, we prepare the operation. As part of that, we have the doc mapper. So this is the current field mappings. We have the source. We use the mappings to parse the source, turn the sort of JSON input into a Lucene document. The Lucene document is contained within the parsed document. Parsed document has, the list of Lucene documents. Well, actually, no, these are OpenSearch documents, which, they contain indexable fields, right? A Lucene document really is just a list of indexable fields. So we prepare index, and then we call index, and this is code that we saw before on the primary. So this is the thing that's going to take the engine. We call engine.index. I'm going to kind of quickly click through this. I'll just get to, I think we'll wrap this one up again with the mention of down here in the index method. We shouldn't end up in here because the operation origin should now be replica this time. So we're not going to generate a sequence number because we should already have a sequence number. And the plan should include this index into Lucene with adding stale operations. I'm not sure what those are. Stale operations I don't think are those no-ops that we identified before, related to operations that failed on the primary, and we want to process them as no-ops on the replica. I'm a little bit curious to see if that no-op ends up using a different plan so that we don't index into Lucene. Possibly. I wouldn't be surprised. But and then we call the index into Lucene, which, as we said, calls add docs, and the call to add docs is what calls either indexWriter.addDocument if it's a single document, or add documents plural if there are nested documents. So now we've covered how the replica ends up writing documents into Lucene in the document replication case. Cool. I'm going to wrap it up there, and we'll see where we go next time. Maybe, I don't know if we need to cover the response path, because we've already covered, shard bulk operation comes in, gets applied on the primary, gets replicated out to all the replicas, that returns back to the primary, which can then respond back to the coordinator. The coordinator is getting these responses potentially from multiple primaries if the bulk operation from the user contained operations for multiple shards, which is usually the case. And then, we return back to the user. So, I'm not sure if there are any other particularly exciting cases to cover on the normal indexing path. Maybe this will be it for the indexing series. So thanks.